So thank you everyone, and this will be like one of the seminars of our reinforcement learning course. And in this seminar, I'm going to talk about some kind of a topic specifically about data efficiency and the probability when you try to apply some kind of automatic control theory, and when try to integrate that kind of method with reinforcement learning stuff. So basically, this seminar will consist of, I would say, probably three parts. And the first, I will have some kind of a revisit to the some successful stories of reinforcement learning to pin down that what's the crucial actors to make them work, and what type of problem that the existing reinforcement learning is good enough to solve them. And also, of course, what's the limitation, what's the other assumptions that are too strong enough for us to use that in many kind of real systems. And also I will talk about a little bit, probably a little bit of pedagogical materials on how control people generally look at this type of problem. What's their methodology? What's their terminology used to describe and to solve the problem? And I think probably for many of you, if you have some kind of control background, it's somehow kind of easy, but I still want to include some kind of that kind of rudimental materials for the people who are not familiar with this topic. And then probably I will go down with some kind of recent progress that from a little bit a mix of optimization and a control field, and will include some papers from others' work, and how this contributed to the theme that we're going to discuss today. And also I will talk a little bit about our own research on happening in the RPL, and specifically how to resolve it with some kind of provable reinforcement learning and with some kind of data efficiency. So yeah, let me see if I can use. Oh, okay, this is a way to switch that. So I think that many of you have seen this kind of pictures from time to time, because probably this is one of the most symbolic achievements for modern reinforcement learning, that it resolves some kind of a really, really complex game. So people try to extract what can we learn from these successful lessons. So basically, if you look at the problem that's this kind of a deep reinforcement learning successfully addressed, including that playing the StarCraft, and also playing the Go, and also chess, a lot of it. So you see that most of them have some kind of properties that are very unique to this type of problem. The first one is that basically you have some kind of access to an exact model. It's like when you place a stone, you know that's what is going to happen. It will kill other stones, or you cannot place there, because these rules are somehow too simple to be simulated on your computer. And also another important thing is that it's also not that difficult. It's not that costly to query such kind of model. It's basically that I'm placing this. I just changed a bit in my memory to represent how this is the status and what's going to happen in the next. So these kind of properties can allow us to do a huge amount of offline training. That's this proved to be very efficient. And even when the problem looks like a bit as complex as Go, and people usually describe to say, oh, you have many possibility as the number of the atomic in the universe, but still we show that if you throw enough computational resources to this kind of offline training, and you can manage that. And also an important question from this AlphaGo success is that it's also important to incorporate this online planning, you somehow merge what you get from this offline estimation of your value function with some kind of tree-based search online. So, and which might be crude, but if you combine it with some offline estimated value function, this becomes very effective. So such kind of properties actually, unfortunately, do not exist in many of the systems that we are interested to control. Like for you are trying to control a robot that can do some very skillful locomotion in the world, that you basically don't have very good model. You cannot exhaustively enumerate all of the possibilities that the robot will encounter, right? And also sometimes you have a system, but the system is kind of huge, and you cannot pay the price to say that I'm trying to do some trial and error on some kind of great system, right? This will be like kind of yeah, this is something then unthinkable, that if you just want to reuse the techniques that we use to build AlphaGo. And also sometimes that this system is probably, I don't know if we can say that we can have a very good mathematical description. It's like you are trying to model the financial market. I mean, if we manage to do so, I think that's a lot of kind of people could be super rich. And also this gives some questions that's yeah, you probably have some very limited data for this kind of offline training. And also this becomes kind of a really problematic if you want to do online learning as well. So I think that's in the last lecture, Ali, like Ali's lecture was talking about some kind of a possible solution. That's how can we let the reinforcement learner to learn from some kind of data set that are collected in a separated stage. So you can avoid to do this kind of repetitive environment query. So yeah, you somehow avoid wearing out your system and avoid paying the expensive cost to do so. And also you have some kind of a meta reinforcement to say that, okay, I managed to train something that on some kind of a task by paying a huge amount of a cost, and like kind of yeah, the data is probably not that efficient. But for my target tasks, I can manage to adapt what I already learned with just some kind of a few short learning. So these are some kind of I would say that still very active research, and you see that from Ali's lecture, but still there's a lot of kind of ongoing challenges to be handled. Yeah. So what I'm going to argue today is that let's try to take a step back and look at this with the perspective of like the general principle for practicing reinforcement learning. So this is probably some people, almost all of the people working on machine learning are familiar with. It's like that, yeah, you have basically have the trade-off, like to have more, if you want to learn from limited data, you'd better have some kind of more domain knowledge. It's like when you try to feed some kind of that's a very classical example. I think it was the real estate price, that you try to have a bunch of features, but you assume that you are just trying to feed a linear model. So you somehow restrict the model you're trying to fit the data, and by doing so, you somehow limit the parameter space you can try to search, so by doing so you can avoid somehow alleviate the overfitting problem. So this is, I think that's quite general knowledge people know. How can we apply this in this context of the reinforcement learning? So one way, like we can imagine, okay, we can try to learn from more data, right? I mean, in this context, is like, well, if my real system is expensive to query, then probably I should rely on some synthetic data from the simulation. And this is actually, I think, a very hot topic right now is about doing this kind of so-called sim to real. And the main challenge is how to mitigate this gap, because your simulation is still a simulation. It's built upon some kind of computational model. It's not necessarily reflect the reality and have a lot of unmodeled effects. So basically, you have some kind of a techniques trying to learn the policy robust enough to do some kind of domain randomizations and carefully modeling your dynamics at different components. And also another thing is that if you not just trying to handle a control with the access to real estate, but have to dealing with some kind of perceptions, and this also has some kind of a gap between the perception, this kind of a rendered image, and compared to the real image. And there are a lot of there's a lot of active research there. So I think that one of the probably most remarkable achievement along this line is this is the work that's from the ETH by learning this kind of local motion for quadruped robot to do some kind of hiking in completely kind of random areas. And this robot is completely trained in the simulation and do some kind of so-called zero-shot generalization. You can immediately deploy that in the domain and to make this robot to handle different type of the terrains. Is probably never you probably never presented. You cannot also be presented that in the simulation. But if you really look at it into this work, it seems that this more general data has to be generated with more knowledge, and it's one of the most key contribution of that work is that they develop some kind of very specialized simulation called the rising, and they have some kind of unique contact model to have very computational efficiency and with high fidelity to model how when your foot is in a contact with different type of terrain model, and more importantly, I think this is one of the main message I learned from that paper is that you have to be careful about the modeling of the actuator dynamics. I think in that robot system is the so-called serial elastic actuator. So this is somehow a little bit different from the electrical motor you regularly use for a lot of manipulators. And this dynamics, they believe that you have to have some kind of explicit model about that. And you also have to do some kind of informative design about the disturbances in the simulations and choose the parameters to do the randomization. And there are also some others, like to say how to build some kind of a course with increasing difficulties in terms of the type of the terrain that the robot should work upon. And also they are not doing I would say that the entire reinforcement learning from the scratch, but have some kind of a teacher networks first trained with all of the information that the simulator was using, and have a student network to learn from the teacher, but only have the access to the sensor information that the real robot can have. So I think that this gives us some saying that okay, it's possible to train with more data, and the data can be synthetic, but still you need a lot of kind of knowledge. And the other way is like let's try to choose the right model to feed our data. And in this context, is basically to say try to use the right policy, right? Because here, like it's the policy we are trying to learn. So we probably see a lot of kind of examples that you probably have a tabular representation of your policy. If everything is discrete, your state is discrete, your action space is just enumerated that where to place your goal stone. And also a lot of deep reinforcement just use a neural network to represent, which is a really a powerful model that can have some high capacity. And sometimes that's if you are aware that your input to the policy have some kind of structure, is say that it's an image, then maybe we should use some kind of a convolution neural network. So you do have some kind of a warrant in terms of the policy form, but usually they are still, I mean, I would say that's rather limited. People mostly just assume that, oh, it's just a neural networks, right? But in the eyes of some control engineers, or I would say that the robotics people, this is not the case. I mean, we managed to control robots and even very complex system way before the appearance of deep neural networks. So basically, you can, if you look at back, let's say what people used in this kind of a domain, you have some kind of a control diagram, you have some kind of a dynamics model, and how to do that inverse and forward kinematics, a lot of analysis in terms of the geometry and the contact models, and yeah. Or you have some kind of a big optimization that can be, but you can convexize that, and you can run that in the real time, and you can use that to control rather complex systems, just like the humanoid robot of Atlas. So this seems that in their eyes that we already have some form of the right policy. I mean, or I won't call it probably right policy, but already policy with some effective form to control really complex system. So why can't we just use that in the context of the reinforcement learning, right? So let's probably have some kind of warm up with some kind of like a notation I'm going to use in the following up slides. That's to see that how people mostly in the control domain, how do they view this problem. Actually, you may find that actually you have very similar problem formulation between reinforcement learning and optimal control. So basically, that's in reinforcement learning, you call it like state and action, but in optimal control, it's state and control. You probably use different kind of alphabetical letters to represent that. And in reinforcement learning, you try to maximize some reward, but in optimal control, you try to minimize some kind of cost. But it's basically like it just can be correlated with some kind of negative sign, right? So I would say the most critical part is that in optimal control, you generally assume a kind of a nominal model there. So this allows you to write down the entire optimization problem. But in reinforcement learning, you assume some kind of Markov decision process, but generally you don't assume to access to that. So that's why I'm highlighting here. That is, although the problem formulation can include this, but yeah, in reality we don't really have the concrete form. But this is not the case in optimal control. And of course, optimal control might also involve some kind of constraints on your state, on your the control input. You should not apply too much control input. You can write down some other constraints, but let's just stick to the simplest the form with just the dynamics itself. So,
sorry, excuse me.
Yes.
May I ask a question here, or you would like to take question after? Okay, great. So could you please go back to the previous slide? So I have a quick question about, yes, I have a quick question about the optimal control. So could you please elaborate the dynamics equation? So is that always available for optimal control?
This is like I'm going to talk immediately. It's like I'm writing in a most general form. It's like it's just in the F, but usually we can assume some structures there. And if you say really doing some kind of numerical solver for this optimal control, of course you need to, because this is one of the equality constraints. You need to give that to the solver. But from the learning perspective, if we know some kind of structures, then you can already parameterize your solution somehow, and this you can leave that for the reinforcement. And I think that's the whole idea I'm going to cover in the second half.
Oh, thank you. So that I will be patient. Thank you. Yeah.
Thanks. And I think because this is a really good point, I'm going to touch very immediately. And but before that, let's see that how people generally view this type of problem and how this can be connected to our reinforcement learning. So I would like to give some kind of revisit to our value iteration. I think I hope that you still remember it from us the introductive lectures. So basically, it's kind of write down this kind of a Bellman equations, but you use some kind of a maximum operators, and to say that this is a way that how we can obtain an optimal policy. And I mean the optimal the value function corresponding to the optimal policy. But of course, if you have this this value function, you can easily to derive your optimal policy. So this is what happens in the reinforcement with value iteration. And I will say that in optimal control, you have something very similar. But most of the time, the optimal control probably you see that we're more trying to deal with some kind of continuous systems. That's you have some kind of a time derivative of your state. So your cost function is somehow the integral of that. You also have discrete version as well, but for the theory derivation perspective, I'll just stick to it. So basically, you can write down a similar equation in these scenarios, and it's basically to say that now your value function is the integral. You can imagine it's just the sum, right? And you try to do this kind of minimize here, because now you are minimizing the cost function rather than maximizing reward. So basically, this just change the mass to the mean. So I mean, and then you can eventually have a kind of a relation like this. This is the so-called the Hamilton-Jacobian-Bellman equation. I'm writing in a more general form because you can assume that this value function is time index, but if it's a time invariant, you can imagine this part is zero. I will revisit to this point. So you can see that it has a very similar structure to our value iteration thing here. Is basically that this max change to the mean, and you have the running cost here, you have the instantaneous reward here, and you have the what's going to obtain if by running this current policy for the future step. And similarly, you have this where this kind of your dynamics model it is part of the story. Okay. So how this is derived? I mean, I will keep it as a bit informal, but some of you might be a bit curious because this is a continuous. Why you need like a here is like you have the direct the form of the value function, and here is the partial derivative. How this come into the picture? So basically, that's it's very simple. That you just assume that you look ahead with a small time interval, so you can write down your Bellman equations in a form like this. This is what you accumulated with your running cost within this time interval, and this is what you expect to get for the remaining time steps. And you do some kind of a Taylor expansion of this one, and you can write down. So you see that all of these kind of terms start appearing, and this, remember, the derivative of your state is basically our dynamics models, and of course you have those kind of high orders which we are going to which are going to be ignored. So if you substitute this to that original equation, you will see that this eventually becomes something like this. I mean you can check the proof later, but yeah, that's basically what's happening here. And of course, what you can imagine that if we divide this kind of a dt and takes that to 0, basically this integration will just disappear with this internal part remained, and this you basically have what we are just describing as the so-called Hamilton-Jacobian-Bellman equation. That's why you still have a Bellman here, because yeah, they are basically the same thing, right? And so here that you can see that, like I said, that if your value function is like you use your value, this is in this context so-called cost to go, is like the cost that you are going to incur for the remaining steps, is like your value function in the time invariant case, that this is you don't really depend on t, then this part is 0, and eventually you have some kind of a form of equation like this. And this is one of the core equations I will going to use later. So, but I will write that. I will bring it up on that slide as well. So, is there any question so far? Because this involves some kind of I would say very light mathematical derivation, but still, I hope people are still catching that. How can we reach something similar compared to the value iteration? No question? That's great. Okay.
One quick question here.
Sure.
So here, so does this equation sorry, just this equation, can this one model can this one model the stochastic behavior?
Yes, precise. You also have stochastic optimal control as well. So in that sense, that's okay. Usually you take the expectation of your, but there are also some risk sensitive things. So you also take into account the variance, but I'm keeping everything that's simple. Okay. So in that sense, I think that you also have the expectation here, and you also have some graphical model interpretation to that. But yeah, I can give you some kind of reference if you're interested. There are a lot of like kind of correlation people can see from that.
Thank you so much. Yeah, good. Yeah.
No more questions? Okay. So now here it comes into the picture. That's what I promise everyone to touch a little bit. It's like generally we write down some very general form of the nonlinear dynamics. It could be everything, as long as it's kind of a continuous or something like that. But usually that's we don't deal with this in the control domain. We are more interested in so-called kind of control affine dynamics. So basically you have a structure like this. It's still linear, and then you have some nonlinear part. It can be arbitrary nonlinear part. It's kind of a drift. That's how this state should, I mean, naturally evolve with when your will control input is 0. And you also have some kind of so-called like kind of gains, so like kind of you apply some kind of a multiplication to your control. But most importantly, it's like yeah, the entire like kind of system, the derivative of a state is some kind of linear with your control, with your U. So this is not non-linear correlated here. You may think that this is something like, oh, is it too limited? But surprisingly, that's actually, you can use this to describe a lot of motion equations and even very complex physical system like what I'm showing here. So, and even, I mean, if you check like with the technical document, a lot of physical simulator like Mujoko, what's behind is some kind of a motion equations like this. So you can see that you can write down to say that this control input and your contact forces are really like kind of following sub this kind of relations. So because here you have some kind of a nonlinear part, but it's still linear with your control forces. So I'm trying to convince you like that yes, this is we do have some kind of structure start to being imposed here, but it's still a really powerful one. You can use that to describe a lot of stuff. Okay. So, and then this is another structure we are trying to impose. Now this times we apply this to the running cost, or you can think that the negative of the reward function. So here we are assuming that, okay, we still have a nonlinear part that can be arbitrarily parameterized, but it has to be only dependent on the x. And you also have some kind of a part to say that, yeah, related to your control effort, but this has to be quadratic. And again, you may imagine that, yeah, this looks not like an as general of our for general reward design, but actually, if you really look at like a lot of gym tasks, a lot of like reward design also follows some kind of form, because that's basically to say that you can describe the desirability of some kind of state, and also at the same time to say, oh, I don't want to pay a lot of control effort, right? That's basically what happened in a lot of cases. So this is like kind of another important assumption we are going to make. And if you take both of these kind of assumptions and use them in this kind of Hamilton-Jacobian equation, you can find something very interesting, and which will significantly simplify our problem. So basically, like what we say, that now you replace this very general function with this not that general, but I will try to convince you this is still general enough, and also basically replace this original highly, I mean, very general nonlinear dynamics to this kind of a control form. And all of a sudden, probably someone already see that, because this kind of optimization is performed over this kind of control and is not dependent on some kind of nonlinear part, and we can ignore that. So that's what's really happening here. So eventually you can see that actually this part is basically a quadratic with this kind of control. So that means the evaluation of this function is like taking the maximum of your the maximum operation of your value iteration steps. Actually have a closed form solution. And remember, this is a little bit important here, because for in terms of the value iteration, if there's a discrete, you can basically enumerate that. But here is a kind of a continuous, but you still manage to have some kind of a closed form solution. That means if you just assume that your dynamical system following this, and your reward function, or you say your cost function is following some formula like this, actually you can write down what's the desired control policy looks like. It's basically a formula like this. You still have a lot of unknowns. It's like, okay, like I said, if you have this kind of a real value functions, you should develop your policy, right? But still, this gives you some kind of a form, some kind of structures, which is not just like kind of a black box of neural networks. Make sense? Any questions regarding this part? Because this is probably a little bit getting into the. No?
Super
Great.
cool. And I just have like a, can we go back to the previous slide? I just like have a insight question regarding the structural loss function. So how do you think the CX could be, is this one actually related to the energy, something like that? Because CX seems like potential energy, and the EU seems like velocity, seems probably like kinetic energy. Is there
This
any...
is again, you will see yet another simplification. I mean, here is we didn't say anything about this CX, so it's just to say it's a reward defined over state. But as you said, if you carefully choose that, you can do that with some kind of energy shaping to say that okay, this should go to a certain kind of equilibrium point, which I'm going to again
super cool
in the next slide. Yeah, this is like a very exciting part if you connect it.
Yeah,
see that how people perceive this from another perspective.
Super cool, thanks. Yeah.
And yeah, like what I promised, this is like let's take a further step to say okay, this is still too complex to me. I mean, I will just have a kind of a linear form. Now it's like to say that okay, this part is a drift, fine, but I cannot tolerate a nonlinear form, but it has to be a linear one. And this one is you still have the gain, but the gain is no longer dependent on x. So it's completely, you can see that it's kind of a linear equation now. And yeah, like Rebert just commented, it's like this can be described as some kind of energy function to say that okay, we have some kind of a quadratic energy, so you can imagine some like a ball-like thing, and where I'm expecting I will penalize if you are deviating from some kind of equilibrium. So this is I would say that for a lot of people having some kind of a control background, I mean, problem from the undergraduate level, this is a very famous form, so-called a linear or quadratic regulator. Regulator in terms of that this state is expected to go to some kind of origin. And this is some kind of a problem that, yeah, you can imagine this is a very, very simple. It's basically like a quadratic programming here. And we don't even consider some constraints on your input bound or something like that. So for this kind of form, like I said, that in the past slide, in the last slide, we don't know that you still don't know that what this kind of value function could be. But in this case, yes, you can write it down. It's yet another quadratic function with this x, and which is not complex to derive that. But if you look at any kind of control textbook, it will give you some kind of very concrete thing. So that basically means that you used to have some kind of a nonlinear solution, right? Nonlinear policies, like this part can be nonlinear, and the derivative could be of some kind of an arbitrary complex value function is probably another nonlinear thing. You combine them, this is a nonlinear thing. But if you assume this kind of thing, you eventually have something that is linear. Because remember, this is just the parameter of the value function. Once you have that one, it will not depend on x anymore. So eventually, in this case, you have some kind of a linear policy. So then the question is linear policy really useful? And maybe to a lot of people's surprise, the answer is yes. Because you can imagine this is a little bit scary, because if you think that, oh, I probably need some kind of really complex neural network policy with a lot of parameters, with strong capacities to encode really complex behaviors. But for linear policy, what type of motion you can represent? But you can think in a way like that. It's like you can always actually differentiate your nonlinear dynamics. Of course, they have to be kind of a differential, continuous, and we have some kind of a local linear approximation. So that means that if we really have some kind of a target behavior, so they target the trajectory you are trying to follow, it at least should be locally controllable with some kind of linear policies. And if you don't believe that, and someone trying to really show that to you, it's like this from that really cool work from the Professor Benjamin Recht, and they actually show that for a lot of I mean, probably I won't use the word, the seemingly complex gym tasks, you can just learn a linear policy to do that. And you also don't have to use those kind of like kind of a popular reinforcement algorithm like PPO and SAC. Basically, you can just do random search, because here you can see that your linear policy only have this parameter of the K, right? And what they are suggesting here is you just do random search of this parameter. This is only the linear parameter, which basically like kind of, you see that the algorithm is basically to say, example a bunch of things over this kind of the entries of this matrix and do something to say, okay, this is my perturber policy, this is my perturber policy, and I try to run all of them and see that which is performed better. And you rank them, select something that's is promising, and then you make a like kind of update step. So you may see that this is probably a little bit like a stochastic version of a finite approximation of the gradient, right? Because you don't really have the gradient of the environment or this kind of thing, but still you can try to perturb some kind of the parameter, you try to optimize and try it out and do some kind of approximation here. Well, this is what basically eventually happening here. But of course, they have some kind of tricks to say you have to normalize your reward, this kind of thing, and which they demonstrate is the key to the success. But the general idea is to show you that for a lot of kind of gym task, you can see that they tried all of kind of standard module task. You don't really need a neural network policy with that scary of amount of parameters, and you don't also just run some very simple random search. This is like a bit mind-provoking. I would say that's yeah, and you can see that they even managed to learn the really challenging task like the ant and the humanoid. Of course, for the humanoid, they need some kind of a small adaptation, which is I think falls into this kind of version 2, but generally this message holds. Yeah. So hopefully this can give you some kind of idea that's okay. Don't underestimate the power of a linear policy, which might looks a little bit yeah, too simple, but actually yeah, it's probably more than it can do something more than, or like the argument from the paper is that, oh, probably these benchmarks are not really good benchmarks for reinforcement learning. They are not that challenging. We need something more, or maybe I don't want to have a firm conclusion in terms of this. Yeah. So shall I continue, or any question regarding this last part? No, that's great. Okay, so we see that you can manage to say that if you have some kind of structures about your dynamics constraint, you have some structures about your running cost, you can boil down to some kind of closed form solution that you can write. You can use that for as the the form, I'd say the right model of the reinforcement policy you are going to train. But most of the problem, actually, you can imagine that it's probably you don't really have a closed form solution, right? But that doesn't prevent us use that as a policy, because a lot of people, I mean, there's some kind of a trending topic is so-called the differentiable optimization, because eventually you solve some kind of optimization problem, you follow some kind of gradient steps, these can still be represented as some kind of computational graph, right? So if you use some kind of automatic differentiation or some more smart techniques, I'm not going to talk about that, you can still get some kind of a gradient of the solution of your optimization. So that's basically to say that your policy itself, you evaluate the policy, your inference of the policy is solving some optimization problem. And you can take the gradient throughout this entire optimization process. So this basically means that what I'm trying to describe is entitled that, yeah, you can embed this kind of entire optimization as your policy. Actually, this idea, I would say that is not very new. It happened even before the appearance of a deep reinforcement or deep neural network thing. And so people already, I think this is a little bit more from what, from a bit close to neuroscience thing, because they call it some kind of a motion primitives. Basically, the idea is like to say that, okay, you have some kind of a motion representation, but this motion representation itself is a planning problem, right? I mean, they are not tackling the most general form like the dynamics constraint. They are mostly like kind of to say that have some linear thing, localized and quadratic cost, but still the idea holds. It's basically to say that when you try to evaluate your policy, you have to do some kind of internal trajectory optimization. And unfortunately, at that time, I think they don't have the access to some automatic differentiation packages. So yeah, they basically to do some policy search to like what that simple policy search that work I just showed. They basically sample some kind of trajectories and run this optimization and take some kind of control and evaluate that with so-called extrinsic cost, because this is not necessarily the same one as the one you use for your internal optimization. And this tells you that which parameters of this optimization problem is better. So basically they are doing, yeah, it's kind of, you can imagine, it's kind of an evolution strategy for doing this kind of a policy search. But this is but I think in this paper, they already show that this type of representation of the policy had some kind of nice properties to better to generalize, change the goal or something like that, but was in some kind of a infant period, I would say. And then obviously, that's like I said, once you have this kind of automatic differentiation to handle all of this gradient for us, then people start to, okay, then why not just like kind of expand this kind of gradient steps? And so you can imagine it's like kind of a recurrent neural network thing, right? So, and you back propagate all of this kind of thing and to your initial observations, and then yeah, you use this kind of a policy they call the so-called universal planning networks. And differently from that one is that you have some kind of encoder. So that means you can handle some visual input. And again, in this paper, they show that for a policy with such kind of form, it's generalized better. I mean, generalized better, not for completely in reinforcement learning, because they most demonstrated for imitation learning. But they do show that if you train a policy with imitation learning, and you can reuse the internal cost function here for reinforcement learning, and that gives you some kind of efficiency gain as well. So that's kind of like in a continuation of this kind of ideas. And yeah, you can see that it's indeed makes sense to consider some kind of policy like this. And also, there's probably a little bit of more recent work is, yeah, people try to avoid this kind of expansion of the optimization, because that's why, I mean, that's why in this work, they didn't really use that for reinforcement learning, because you can imagine for each kind of a policy query, you need to solve the entire optimizations. And especially if you have a really long time horizon, this neural network will be huge. So basically you do that for offline training, but in this case, they are showing that at least for the backward part, means that we can, when you evaluate the gradient, you don't have to really follow the automatic differentiation thing. And if you imagine this, you can realize this by invoking this kind of implicit function theorem. So basically to say that, okay, if we assume that our forward evaluation of the policy here is like in resolving the optimization, give us some kind of optimal solutions, then this solution should fulfill some kind of optimality conditions. And by differentiating these conditions, we can find some kind of relations between the parameters we are going to take derivative with respect to the with respect to the optimal solution we obtained from the forward path. So basically, they show that yeah, your backwarding can be more efficient. Yeah, and basically, if you look at the math, they just prove that for the backward part, you just construct another LQR for these auxiliary variables and to solve that, because we already show you that LQR is somehow very simple form, you know, the solutions in the closed form. So this can be very efficient. And people do show that this is a very strong, it is a very powerful idea that, yeah, you can have this optimization for addressing some kind of, for learning some kind of a little bit more than toy problems. And this clearly to show that for the backward path, they can have some kind of significant significant gains from this kind of traditional method to just relies on automatic differentiation. But they do have some kind of limitations. So usually they find that, while you cannot just use neural networks for your dynamics constraints or policy represent, that's always, usually that makes the problem a little bit harder, right? Because you can imagine that when you have some kind of neural networks as part of your problem usually is a kind of a non-convex optimization. And you just don't know that if these forward steps can give you the global optimal solution or not. So if that solution is not accurate, you probably cannot expect the differentiation will give you the correct gradient. The best you can get is, okay, it's kind of like the surrogate of my gradient. I roughly follow that. Hopefully it can improve my performance. But if there is a kind of neural networks, these things are a little bit becomes more trivial. So becomes a little bit more non-trivial. So in their works, so they show that usually you need the dynamics parameterize the dynamics. Means that, okay, for robot arm, I just cannot model my robot arm with neural network, but I need to explicitly write down the equations with the length of the arm. This is the joint, and yeah, you can have the parameters about the length of the arm, but this cannot be just through modeled by throwing a neural network there. So this is an issue that people start to think that, okay, so it seems that the core issue here is that the non-convexity from the optimization from the neural networks. So why not using a convex optimization? So there's a like kind of a benefit from this. The first is that we know that it's already usually fast to solve a convex optimization problem. So that means that your policy can be evaluated, yeah, almost in real time. So you don't really worry that when it will be converged or not. And also we know that for convex optimization problem, you don't need to worry about suboptimality. So once your solution somehow converges, there should be that. There's only a unique solution to that. So this is something that people have. You indeed have some code repositories covering that to give you some kind of differentiable layers to allow you to differentiate through a convex programming. So this here, I mean, they only show that in a toy example to say that, okay, I'm trying to learn this polytope parameters, and I have some kind of example the data to say that this is my solution of my optimization problem, and what is the right problem parameters correspond to that. So you can see that by following the gradient of this, you can manage it to have the initial guess of this, but eventually converge to the true one, which is like kind of a really cool toolkit, I would say. Yeah. But of course, the other problem is that, yeah, convex optimization is still limited, right? I mean, it's like we talk about like that can control affine dynamics. We didn't say that they have to be convex. So how can we have some kind of non-convex dynamics come into the picture? We still have to handle some non-convex dynamics constraint here. So one of the most recent, I will say not most recent, but in recent years, that there is some kind of a methodology called Kuhlmann representation. Basically, they are arguing that we can trade the complexity from nonlinear dynamical systems to a high dimension representation, but with some kind of a linear evolutions in that space. So basically to say that, okay, I have some kind of a transformations which can be parameterized by some neural networks. Actually, as you can imagine, if there is some kind of a thing we want to learn, we give it a neural network. And then after transforming this from my original state space, and I end up with another state, a transformed state. And this transformed state, there's some kind of theory tell me that you can estimate a linear, approximated linear, because usually it's like an infinite dimension. You can imagine this the theorem from like kernel spacing. But generally you can still have some kind of approximation to say this approximation can be a linear dynamical system. So if you can, so then you can imagine that if I try to design some kind of a cost function in this transformed space, say as a quadratic form, then you will have an LQR form in this transformed space, which is like corresponding to the original state space. But now this time it's LQR problem, and we know that it can be efficiently solved, and we can even write down the solution of the closed form solution. So you can see that this is something that's basically what's happening here. You have this kind of a state, and you go through some kind of a neural network representation, which we are going to learn. And then this one will subject to this kind of LQR problem. So you can just have a non-linear policy on top of it, a non-linear in the original state space. But you have some kind of optimality structure there. And this is one of our submissions, and we show that, yes, such kind of a policy also learns a little bit better than this kind of the neural network policy you always use. And use also, because this is kind of an optimization, we didn't really assume that what the dynamical system should look like, so we can apply this to some kind of a robotic platform without much assumption about how it should look like. So basically, you can imagine that this is some kind of, we are doing some approximation for the convexity, and because we know that for a convex optimization problem, this have some nice properties if we use it for the policy. But still, we want to have some kind of representation power. So in that sense, we can integrate a neural network representation, allow us to do so. Okay. And also, this is showing that the benefit of having this kind of LQR form, that's yeah, you can run this almost in real time. That's what we show, that you can actually use that to try to control some highly dynamic task like pivoting that to some kind of a goal state space, which is unfortunately not possible if you are using those kind of UPN thing, because yeah, usually that they are much slower. So, there are any questions regarding this part, or?
Yeah, may I ask a question regarding the Koopman representation?
Sure.
So why do you say that this is an approximation? So for example, for kernel methods, it's actually equivalent, right? So why? So
in theory, yes. I mean, if you really write down this, so you cannot, basically your transformation should map your original state to let's say the infinite dimension space. It's a function space.
Yeah. Mm-hmm.
But eventually you have to use some neural network, give you some output with a number of like an output thing. So it's kind of, for some kind of a problem, you can say that I think you can prove that this is an exact approximation. But most of them you just can't. So it's kind of I think there is a good argument for having this, is that it's like kind of you are trying to have an exact solution to an approximated problem, comparing to have an exact solution to an approximated solution to an exact problem. It's like, I mean, it's a little probably. It's like for the original optimization thing. It's like, I know the exact problem, how it looks like, but I mean, I'm not talking about convex, but the non-convex thing. So the best you can have is some kind of a non-optimal solution. So it's definitely an approximation. I would argue that probably this is not a good idea comparing to this, because you are still learning your problem here, right? So your problem, if your problem is exact, is still questionable. So why not just like an approximated altogether and just have the exact solution to this approximation?
Yeah, I think it's really cool work. Another question is that, so could you mention some limitation or drawback of this Koopman representation?
Exactly.
In practice.
Like you see, that's this needs some kind of a model estimation here, right?
Yeah.
So that means in your reinforcement learning, you should have some auxiliary cost to say that, you have to fulfill these constraints. To say, some constraints like this.
Yes.
And if then you start to have some kind of trade-off that this dominant, and I will tell you that it indeed happens. It indeed happens. And another problem is that there you have some kind of numerical issues by applying this. It's not related, it's not restricted to the Kuhlmann representation, but it's basically like, if you have a really long time horizon, imagine, like I was saying, I'm talking about 100 and 400 time steps. So imagine that what happening is like you have some kind of parameters of this A and B thing, and you recurrently apply that. You have some kind of a very deep neural networks, and you tend to have some kind of gradient exploding problem, which is not unique to this. If you check some kind of recent papers from Google about like what's the title of that? Is differentiability all you need or something like they pin down this kind of issue happens almost everywhere. I would say that as long as you involve some kind of a long-term expansion, this happens. It also happens here. So basically, it's like this. For this one, I think that you can use like 20 steps, look 20 steps ahead. It's like basically you have probably 20 layers of your data. And beyond that, yeah, it becomes a little bit problematic.
I see.
And also, if you look at the dissolving of this LQR problem, it involves some kind of inverse of this matrix, I think.
Inverse matrix, okay.
Yes, this means that you are differentiating from the inverse matrix, and this becomes a more problem, especially if it is a high dimension. So I didn't manage to use this to learn humanoid, because for humanoid, the input dimension is much higher than this. And it's just explode. So
computational expensive. I see. Yeah.
Yeah, and also expensive, of course.
Yeah.
But that's already because here you can see that this part, once you train your policy, this part can be separately evaluated, or you just evaluate one batch.
Yeah, I see. Definitely,
it's not really a big issue, but I would say that it's not solved everything. It's you still have some kind of force.
Yeah, but super cool work. Thanks. Yeah.
Thank you. And I don't know. I mean, oh gosh, I don't know. Chris, should we take like a rest or what? Or we should continue probably. I think I probably need to forward a bit faster, because probably I still have half slides, but yeah, let's see how much we can do. So welcome back, and so probably we can call it the second half is more about like not just about that learning with efficiency, but more about like the topics of can we also learn with some kind of provabilities here. So this part is more focusing on some kind of robotics dynamical system. So it's like you can somehow like have a more breakdown to your control of fine form to some kind of manipulator dynamics here. That's I think for robotics people this looks like already quite familiar, but you can check that this actually also follows a form like this. It's just like you have some kind of concrete term about your mass, about the kind of like your gravity, how to write down this kind of all of kind of things. Yeah. Oh, I'm not sure if everyone is seeing the slide or.
Yes, we can see everything.
Okay, that's great, because I just see something pop up. I saw that I missed the last part. Okay, so it's like what I mentioned, that even before this kind of learning methods becomes kind of a thing, that's we already know how to control this kind of robot system, right? So there must be some kind of structures. There must be some kind of domain order we can use here as well. Let me see why I cannot. Oh, okay, sorry. So one of the critical issue that I would say a lot of robotics people is dealing with is trying to control a motion, not just in the free space, but with some kind of a contact with the environment. Because that in the early days, not in early, I mean, I have seen still that a lot of robots, the application is doing some kind of industrial applications that normally this kind of thing, inevitably you will have a lot of kind of contact. So you have to handle this kind of interaction force. And what's one of the, I would say, very simple ideas to do so is trying to so-called use the compliance control here. So the idea is actually, I would say, pretty simple. It's like, yeah, you will not directly tell the robot what's the force you should take. what you should say, because that's some kind of a complex. You just tell that how stiff, how compliant your motion is supposed to be. It's more a little bit like a human motion inspired, because imagine that when you are trying to wipe out something, you are not exactly calculating some kind of force you try to exert, right? You just try to like kind of stiffen your muscle to say that, this part I have to push a little bit harder. So basically you are doing something like modulating the stiffness of your controllers here. And what they're arguing here is as well. So basically they say that, okay, your neural network should not output a direct force signal, but should predict some kind of stiffness or impedance or whatever you call that, some compliance parameters here. And in this way, your control force will be implicitly decided from this kind of a rule, which is a very simple rule. If you see that again, it looks like, it's kind of a linear policy, right? So that's basically your policy learning is, again, try to find this kind of parameters here, but in this context, is trying to find the right stiffness. So, and this idea actually is also not pretty new. I would say this dates back before like deep reinforcement, and people already use this to parameterize the trajectory you learn with this. That's the pi-square method. It was a very popular method, I think, for reinforcement before we have this kind of neural networks at the table. So basically, they are doing that exactly this. It's a little bit extended to say that, okay, I want to have some kind of time varying impedance parameters here, of course, and the time varying desired position as well. So it's basically you have some time independent solution. Looks still really simple form, and they parameterize this both the compliance parameters and the desired trajectories for each independent of this robot joint degree of freedom. And it's actually very effective. It's if you can learn this kind of control this little dog robot, because that's a little dog, so you can learn that on the real system, but still you with like kind of a significant reduction of the number of the trails you can imagine. It's just like 100 trails, and you can learn some kind of jumping motions, jump over some kind of gaps, which is like pretty impressive, I would say. So it's basically to say that you can learn with some kind of policy with this kind of a variable impedance, variable compliance structure in the mind, and this can be very effective. And this is also true when in the area of the neural networks. And actually, this is a work from the several people that explore. Okay, so you have some kind of compliance control like this, but it's probably too limited, because if this is a fixed thing and if your environment is not following some kind of simple geometry, then let's make it as a state dependent, which makes it more general. Of course, you can say that, okay, this has to be positive definite, but you can handle that with some kind of neural networks here, right? And they show that with such a kind of a policy, you see that it's basically like kind of a neural network times your X again. But this structure works pretty well for some kind of a contact-rich task when you have to do some door opening and do something to surface wiping and comparing to some of the most fundamental form to say, okay, I just let my neural network out to predict what force to take. And this is, I think, yeah, I forgot to cite another paper that's basically doing the very similar thing, but the message is the same. That we are doing some kind of a contact-rich thing, and this could be like kind of a right form, because people or in robotics already know that such kind of controllers are quite an effective form to deal with this type of tasks. But usually control people will ask a question, will you present him or her like kind of a controller is it stable? Because these people like kind of won't have some kind of mathematical guarantees about what the controllers are using to control my robot. And so one of the questions that would be that can we not search the policies just like a neural network policy, but policies with some kind of I'm calling here the inherent guarantee means that the parameters are within some space, that all of this space, all of the policies in this space can have some kind of statement say, okay, they let the trajectory blah 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 blah. So you can imagine that by restricting your search in this policy, yes, you are somehow limited the behavior you are trying to search, but then on the other hand, you also have some kind of guarantees. You also have some kind of, like say, provable correctness about the behavior you end up with. And remember, this also might impact your exploration process, because exploration might be dangerous. You are trying to run some immature policy here. So you want to have some kind of guarantees at the, at the first place. So there will be a lot of kind of guarantees on terms of stability, convergence, consensus, and I will just talk about this kind of have some kind of basic, probably it's also not that rigorous, but for a lot of people, like people with control background, this is also probably very familiar to them. Don't be scared by this kind of math. It's not as crazy as it looks like. Basically, to say that, okay, you have some kind of equilibrium, and if I'm starting with a position close enough to this equilibrium, I can somehow guarantee that all of my trajectories is within some kind of the ball surrounding this kind of equilibrium. This is like the most, I would say, the loose definition of the stability. It's basically to say that your trajectory will be bounded. And this will be important for some physical system to say, I'm pretty sure my robot will not like swing to the air or something like that, because this is something that we want to conclude. And also you also have this so-called asymptotic stability, means that, okay, it's not just to say this arrow is bounded, but this arrow tends to zero. It means that, okay, I'm somehow moving towards to this equilibrium, right? And also if you say that I remove the constraint to say you have to start close enough, but you can start from any point of the state space, then you can say that, okay, this is the globally asymptotic stability, which is probably the strongest version of that one. And if you find it's hard to understand that, provide you some kind of illustrative example. So you see that the stability means that, okay, I'm starting within some kind of balls, and then all of my trajectories is somehow bounded by this kind of another ball. Yeah, but containing this equilibrium. It does not necessarily to go towards that, as long as it's bounded. For asymptotic, it means that, okay, it has to go towards that. By taking what type of trajectories, I don't really care. And for globally, you can see that it's like, oh, for any kind of a trajectory, if I'm following my control policy and my trajectory is governed by these state dynamical systems, it has to go towards that, no matter what. And remember this, here I'm using the most general form of the dynamical system to tell you that actually you can draw such kind of conclusions for pretty general form of dynamics. And how to do that? Basically, that's the general way of, to say, doing some kind of Lyapunov analysis, to say that, okay, if I manage to find some kind of energy function that is, always positive with energy, and also I can prove that the time derivative is that it's like how it will vary along the time horizon will always be somehow smaller than zero. This means that my energy is just keep decreasing. I'm losing energy. This is probably not correspond to the physical energy here, but it's just like kind of a numerical description, scalar description of my system. And if I can prove that this number keep decreasing, then I can somehow draw the conclusion about my trajectory. It will be bounded. It will not have some kind of infinity of one of my state component. And also you can also show that if this is you have the zero, you can guarantee that the gradient, the derivative is zero at the equilibrium. You can know that, okay, that all of my trajectories at least start locally will converge to this. And also, again, if you remove this kind of, say that you had to start with this ball, then you have the global synthetic asymptotic stability. So basically you have, if you manage to construct this kind of energy functions, you can draw some conclusions about your dynamical system. So any questions regarding this part? I think that for control people, this is just I'm talking about some undergraduate materials. No, that's great. You don't need really need a mathematical, but you somehow I'm somehow expecting you to see that how can you craft some kind of policy to fulfill such kind of constraints. And if you see that this is another illustration to show you that if you have some kind of energy function, this is what is really happening. This kind of gradient, and have to have the inner product with your dynamical system, where the dynamical system will lead you. And if this is pointing to some direction that your energy is decreasing, then you can imagine, right? It's somehow like going towards like small so-called attractor basins. And if this is 0, then it will lead your robot towards to that. And of course, you can imagine if you parameterize these energy functions with some kind of, let's say, again, neural networks, then we can try to learn to shape this energy function and to generate a different type of motion trajectory. But all of these motion trajectories will have this guarantee to say they will go towards to this kind of goal. But of course, not all of kind of whether neural networks can fulfill this. And so let's first see that we talked a lot about this kind of controllers used in the robot. And are these, having this kind of so-called Lyapunov stability? And for the most simple one, this kind of linear thing, and it's relatively easy to prove that, for some kind of conditions, and it is. But if you want a stronger version with the variable impedance, and especially like that kind of state one, usually you don't have these guarantees, unfortunately, although they do show that you have some kind of learning efficiency from that one. And this one is probably the most interesting one that you recall that from that HAB equations, you also have the form of your optimal controller. Is that stable? It is stable, and especially if you just have a very simple, not simple, I would say, because you just need your cost function to be 0, but actually this is more restrictive than your Lyapunov function, because if you look at this, your value function here is actually more or less your Lyapunov function, this energy function, and this effectively requires all of this kind of all of the derivative of your the time derivative of your Lyapunov function equals to your running cost function. But generally, Lyapunov analysis just say this has to be smaller than 0. It doesn't have to equal to anything. I would say, So it is stable, but in a more restricted form. I would say. Any questions regarding discussion so far? It's a bit probably more control oriented now, but So this is one of the idea that's, like I mentioned, okay, so if we can shape our motion trajectories by parameterizing this energy function, then let's just parameterize it with some kind of neural network, right? So indeed, you can prove that for a certain neural network function, which is have to be convex, has some unique minimum. This is a neural network function that's mapping from the state to some kind of scalar. If they have this one, then you can prove that you have some kind of equilibrium is low with like the strongest version of the stability. And so it's basically to say that this policy will encourage some kind of goal-directed behavior. You have some kind of goal to reach. But this happens a lot in robot manipulation. So you basically want to insert something. You do have some kind of environment constraint, but it can be implicitly handled by the reinforcement. So this is the like kind of what this policy can provide. And so how can we have this kind of neural network policy? Neural networks have this such kind of properties. So you need people like aware of this kind of requirement, that so-called have this kind of input convex neural networks. And but in this work we need to do some kind of small modifications that make it strong convexity to fulfill some kind of requirements. And also, because we need some kind of unique minimum. Convex doesn't mean that you have a unique minimum, and we need to have some kind of small adjustment to fulfill this. So how does this work? So basically, that's this seems like what we show that in that state-based compliance controller. It works pretty well with this kind of insertion task. I mean, the task is involving contact. And here we are trying to insert a shaft to a hole with a clearance like that. 1 millimeter, I think it's something that's it's not that challenging from the eyes of like industrial people, but yeah, for reinforcement learning, it's like you can imagine that you really need to do the right thing to get into the position. And if you just randomly search that, you probably is just hopeless. And we show that this is greatly outperformed if you just use like a vanilla artificial neural networks. And this is it takes like a little bit more, probably the double the number of the rollouts you need to achieve a comparable performance. And this you can see that it was the behavior. So here is I think the cool thing is that you have both the learning efficiency and the provability at the same time. It means that you are trying to learn from a parameter space that is restricted. But actually, this doesn't sacrifice the capacity of your policy. It's on the other hand, it somehow encourage you to say, move towards the goal that which is really aligned with your task goal. So here you see that, and especially with this kind of stability guarantees, you don't see that this kind of a crazy stuff. Yeah, explored in the gym task, because here for all of the trajectories, even if this policy is not learned well enough, we can still conclude that they are stable. Stable means that yeah, the trajectory will not be that crazy. Yeah. Still the same. So any questions regarding the last piece of work? And no? Okay, let's continue that with this is yet another piece of work that's following the generally, I would say, the same idea, but it's another way to craft the policy with some stability guarantees. So remember that we mentioned that for the LQR problem, this is basically your value function. This is basically you can, your value function, you can use that as a Lyapunov function to conclude about the stability of your systems. But unfortunately, this applied to LQR means your system has to be linear, your function should be like a quadratic signal. So is it possible for us to, say, transform this state space to another state space to make this the stable linear controller, to transform the form of this stable linear controller still stable in this new in this nonlinear form? So this is probably, this is probably a little bit not immediate to say, but if I somehow recall you that people that are familiar with deep generative models, there is a type of model so-called normalizing flow models. It's basically to say that you can apply some nonlinear transformations to a very simple probability distribution like Gaussian, and end up with a very complex distribution. But this distribution, the density form, is tractable. So you can directly maximize the likelihood. You don't have to resort to this kind of variational inference, this kind of thing. Yes, please.
But here, because of the change of variable formula used by this normalizing flow, we lost the corresponding relationship between the points. So it's actually a population or distribution-wise equivalence. Does it matter? Like the states X has a meaning, but it has no meaning in the Z space. So there's no.
Yes, that's actually a good point, because that's where this kind of nonlinearity came into the picture. We want that nonlinearity can conform to our task requirement. That's the flexibility we endure this kind of a policy to learn, right? Or I don't know if this is what you are seeking to.
The point is that, so for example, the neighbor, maybe not neighbor. So let me think a little bit, and then, yeah, I will ask you again later. Yeah.
Yeah. Okay. Whatever. But general idea is that you have something similar happening here. Is trying to apply this differentiable, invertible neural networks, have some kind of diffeomorphism about your original state space. It had to be Euclidean, which is one of the one of the limitations because the robotics you have this kind of IC3 as well. But let's say that let's stick to the Euclidean space, and this allows you to transform that to another space, and then you can check if your controller, the linear system with a linear controller, is still stable enough. And the answer actually is true. Yes, you can have some kind of, let's say that's some kind of a gradient based flow thing that you can easily to conclude, okay, this will be stable because it's linear, we can easily perform the analysis. And if you apply this change of coordinate to this original state space, and if you do some kind of derivations, you can see that, okay, you can end up with a form of nonlinear form of this kind of controllers. And you can still conclude the strongest version of stability proof here, and for, of course, the robot dynamical systems. And so in that sense, you can have some kind of neural network-based controllers, which is supposed to be rich enough, and but also at the same time, it has some kind of proof to say that, okay, no matter what my neural network parameter is, these controllers will always give me some kind of convergence towards this kind of point. It's just like kind of the flow will be changed depending on the alternation of the parameters. And you can see that this is probably a little bit similar to those kind of state-based, state-dependent compliance controller. It's just here, like, this is a difference is measured in the transformed state, the transformed space, but you still have this kind of a stiffness part state dependent. But different from theirs is like this, you have this kind of stability guarantees, and which is I would say that's a little bit rare for this state dependent variable impedance control. And again, that you can show that this helps a lot for you to learn this type of contact rich manipulation task. And again, we show that in the packaging hole. And if you just use this, because remember, this is still kind of a neural network parameterized policy. You just connect to any reinforcement learning algorithm you like the most. It's like the PPO thing, and yeah, and you don't have any constraints on these parameters. So you can clearly see that you can gain some kind of efficiency from that, and also have this kind of a stability guarantee. So here, like if you use PPO, you somehow inject some kind of noise to the action space. So this is what you see the jittering, which looks a little bit scary, but still more or less the trajectory is tending to go towards that goal. So it kind of save a lot of exploration effort, I would say. And this jittering will definitely disappearing when it realizes that it can stably do the kind of insertion successfully. I think it's more or less take the same amount of kind of rollout to learn the kind of a good success rate. Yeah. So any question about the Lux part, or?
Do you have an explanation for the jittering of the video?
No, it's basically, I mean, this is different from the first one. Is like the first one is like kind of say a parameter space. If you explore in the parameter space, but this one is like because you just using PPO, and the PPO will have this kind of a stochastic noise applied to that. So that, but once you learn that, when you deploy this kind of policy, of course, it's deterministic. It would not.
Okay, thanks.
But I'm also highlighting the difference between these two works because it's just using different reinforcement algorithms. The first one is more like that kind of that's a simple random search thing. So okay, then I will move on to a bit more recent work. Is like kind of let's talking about more than one robots, and people can imagine that with multiple robots we probably can do much more powerful stuff, and even with like just two and effectors, if you coordinate that properly, you can imagine you do some kind of really fine manipulation task, even for like kind of watchmaking or something like that. But this definitely comes with a cost to say that, okay, you have a more degree of freedom to control now, and how to certify like the stability for them. And will that learning becomes that easier or harder? And yeah, usually that's this is a kind of an open question, I'll say. So here, I would talk about some very probably important problem that's a multi-robot community. That's people with control background probably also know that it's the so-called consensus. It means that, okay, we have some arbitrary number of the robotic system and they can communicate with each other, or probably following one just a single dimension. But let's say that they can communicate and form some kind of graph thing, and then say they are communicating with their current, let's say, positions, but you can be other information as well. And they keep some updating these informations and apply some kind of control individually, distributedly. And this is crucial because, I mean, the controller for one robot is not relying on the other one. So that means if one of the robots is broken, then it will not impact much to the entire system. And then it's trying to move following this and again, update your information, comment it again. Eventually, you expect to reach some agreement about this information you are exchanging. And here, if it's the position, that means that, okay, we are like moving towards to the same point. So here, remember the difference from that stability, the convergence for stability is here is that we don't know what exact point they are trying to converge. Okay, for the linear system, you know that it probably depends on the initial position. It depends on the initial position, but we don't really care about which the concrete point people, these kind of robots are reaching. What I care is just their relative pose to each other. Like that, they have some kind of a point. You have to meet at some kind of point. Where this point is, I don't care. So this is a so-called this kind of a consensus problem, which is a very interesting that's like kind of properties for this kind of multi-robot system that people want to certify, people want to conclude that as the Lyapunov stability. And it's also actually, you can see that it's actually also can be proved with this kind of invariant set theorem as well. I mean, mathematically they are the same thing. So here, like yes, you see that we have some kind of a linear system like this. And that means that, okay, we can play the trick again. To apply this neural network, this kind of normalizing flow neural network to do this kind of a change of coordinate. Let's see if we can get some kind of a nonlinear behavior. So it means that, okay, we can have some more interesting relative motions to achieve, right? So, and then actually this is true. You can just come up with a form like you see that's a little bit similar to what we have for that the past the last work, and then but yeah, you see that this again works with all of the arbitrary number of robots with second order dynamical system, and you can achieve this global consensus stabilization. Means that no matter where my robot starts, it always somehow meets at a certain point. And also your trajectory can be rather complex because it's parameterized by a neural network. And another critical thing I would like to emphasize is here that symmetry seems like and becomes an important thing. So, because imagine that I want my robots to keep an invariant behavior with respect to the interdistance of the robot. Means that when the robots are trying to behave like this, and if we move the entire team to a new positions, it makes sense to say that they should behave similarly, right? And so this is what happening in the linear form, but not, unfortunately, not happening in this kind of nonlinearized form. And it's because that this kind of function is not equivalent, but you also have some kind of other tricks to do so. So there is a kind of one small modification on this kind of normalizing flow model to make it equivalent under the so-called this kind of anti-modal equivalence thing. It's basically to say that if I have a mirroring my positions, yeah, the matching will be mirrored as well. But this one, you can prove that it works with n equals to 2 robots. But like we said, that even the extent of dual arm coordination can allow you to do a lot of kind of interesting thing. And again, you can achieve this so-called global consensus guarantees. like no matter where my two arms is starting from, if I'm doing some pulling like this, and if I change the workspace position, it will follow the exact trajectories. And you can imagine this will be very useful properties if we want to generalize the learned behaviors from one place to another, right? So this one you can, and yeah, this is probably like a bit of technical detail. How you achieve that is probably actually very simple. If you look at the normalizing flow layers, you just basically need some parts to be invariant and some part to be equivariant. And to do so, you just have a neural network. You don't even introduce extra parameters. You just have some kind of neural networks by summing them, by subtracting them. So you can see that, yeah, they are basically fulfilling this kind of equivariant and invariant thing. And yeah, and so like we said, that is kind of a bimanual manipulation is probably like the ideal validation task for this. And so we can try to learn now to insert by coordinating two arms. So it's like the socket is no longer fixed, but you have to have two arms collaborating with each other to avoid collision, to probably to regulate the contact forces, and try to manage to insert it with a clearance of like 2 millimeters in this case. And yeah, again, you can use like kind of a PPO because all of these controllers are unconstrained within the parameter space. So whatever, like in reinforcement. So does it work? And it works remarkably well because in this task, you can see that you have more degree of freedom to control. It becomes seems much more challenging for the standard neural network policies. So you indeed have increased the reward function, means that, okay, it's figured out I should move these two parts close. But it's like much more challenging to figure out how to coordinate to avoid each other, and then to do this kind of insertion at the end. The neural network policies almost never succeed. But if you use both of this kind of normalizing flow with consensus considerations for both of the original form and the time invariant form, it learns much better. Of course, you have some kind of a large variance. This is all of the reinforcement experiment, I guess. And also, this shows you like the results that it's learned. Basically, honestly, I don't see much difference between these two. I mean, the policy with the translation environment thing here. I mean, if you just evaluate that from the trained positions, they work more or less the same. But if you say that try to generalize to a novel position, means that I'm trying to try to evaluate the policy in a haste that the robots are never trained before, and this kind of translation invariant policy seems to work much better. It's like can still retain some kind of success rate that's even, I mean, in this top layer, I'm even reaching the boundary of the workspace. So I don't know that's when it will start to fading, but yeah, but you indeed have some kind of failure cases. You see that it's trying to recover, but you just don't have enough time to finish the insertion. So this is like the typical failure case here. Yeah. So yeah, you can see that you can have this kind of stability proof, or not stability, say the consensus proof in the context of multi-robot manipulation, and it also benefits the reinforcement. This time it's not even efficiency, but about the success of the task. So I think that probably it's also reached the, and oh, it's already like 15 minutes past. And so here is like the closing note. Hopefully I convince you that it's also important. It's important to provide more data for reinforcement algorithm. It's also important to choose the right policy to optimize. And we do have a lot of great valuable literature from other areas, and I already show you some interesting connection to the optimal control and a lot of some kind of stability analysis from the in the context of the robotics. And this can sometimes, like what I show in the packaging forcing, your data efficiency is so high such that you can directly train that on the real robot. And also another topic is probably over often overlooked is that how can we design a reinforcement system with some kind of provable correctness? This will help us a lot to deploy such kind of system in the wild and convince the people, hey, this learning is like kind of acceptable. We have certain kind of control of that, and we have some kind of theory behind this kind of thing. So it's not just a black box reinforcement learning, black box deep reinforcement learning. And we see that sometimes you don't lose the efficiency by enforcing such kind of certain the certification. And also probably a little bit over foreshadowing that what Chris and Alex will talk about in the following lecture, I guess, is yeah, there definitely should be some kind of connections, because I'm talking about some kind of stability proof also in the control context. But here, like I would say that stability does not necessarily mean that safety. It means that, oh, your trajectory is somehow, well, bounded, but that doesn't mean that you will have some kind of minimal contact force when you have some kind of collisions here. And also, I would say that the form that's here you are imposing is relatively limited. You have to do the analysis for continuous system. You're mostly concerned about the steady performance, and the way of you constraining that is probably not human interpretable. You can hardly to say that, oh, for the time period from T1 to T2, I wanted the state to be there. And for all of the time after blah, 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 I want to, it's probably not that easy. And I think that Chris and Alex will talk about this. Probably, I would say this is a kind of a more powerful system allows us to enforce such kind of stability constraint or some kind of a more concrete, human-friendly task specification. So stay tuned to that.